Okay, it's time to begin. Our today's speaker is Yuri Sachkov, Lorentzian geometry in the Lobachevsky plane. You saw the title themselves. Yuri, you are welcome. Please begin.
Yes, thank you very much. First of all, I would like to thank Professor Krasильщик for the possibility to speak at this nice seminar. Yes, I will speak about Lorentzian geometry in the Lobachevsky plane. In fact, this is a variational or optimal control problem. In fact, a two-dimensional, quite simple one. Sometimes I call it a toy. It is quite symmetric, it is integrable in elementary functions, and everything can be done. In fact, so I'm not completely sure that it is new, so I try at seminars to understand. Maybe somebody knows similar results or the same. But in any case, so I will speak about the problem of finding Lorentzian length maximizers, Lorentzian distance, in the Lobachevsky plane. I will explain this in detail in several slides. So this is the plan of the talk. First, I will recall some basic definitions of Lorentzian geometry. Then I will describe the space where my geometry will live, the Lobachevsky plane. Then I will describe the problem. I will study left invariant Lorentzian problems in the Lobachevsky plane, and then I will start to study these problems. First, I will describe the curvature, and then I will consider it as an optimal control problem, and I will study attainable sets, then existence of Lorentzian length maximizers. Then I will look for Lorentzian length maximizers via optimal control technique, via Pontryagin maximum principle, and I obtain parameterization of extreme trajectories, and then I will describe which of them are optimal. I will show that all they are optimal, and I will describe what we call optimal synthesis. Then I will come back to geometry. I will describe Lorentzian distance and Lorentzian spheres of positive or zero radius. Zero radius is also meaningful here. And finally, I will speak about isometries. So this is my plan. Let me start first about Lorentzian geometry, what it is. So suppose that we have a smooth finite dimensional manifold M. Then a Lorentzian metric is a non-degenerate quadratic form of index 1. That is, in each tangent space TQM, we have a Lorentzian metric GQ, and everything depends smoothly on the point Q. So the quadratic form is not positive definite as it in the Riemannian case, but it has index 1. So if we reduce it to sum of squares, there's 1 minus, and all the rest are pluses. And this Lorentzian metric G induces the following structure. We should distinguish several situations for a tangent vector. So let V be a tangent vector at a point Q, then it is called time-like if the form is negative, space-like if the form is positive or the vector is zero. A vector is light-like if the form is zero and V is not equal to zero, and it is called non-space-like if the form is non-positive. Then you pass from vectors to curves. Let you have a Lipschitzian curve in M, and it is called time-like if it has time-like velocity vector almost everywhere. And similarly, we define space-like, etc., other curves with special causality type. One more geometric construction, we need a time orientation. And time orientation x naught is just an arbitrary time-like vector field in M. And then we can distinguish non-space-like vectors, whether they are future-directed or past-directed. We call V future-directed if G of Vx naught is negative, and past-directed if it is positive. What is the reason of all this geometry? Lorentzian geometry originates from the relativity theory, and here we we assume that information propagates only along future-directed non-space-like curve. In relativity, this corresponds to the following postulate, that the speed of particles cannot be greater than speed of light, and time is not reversible. So we study motions of particles in the space-time. A basic example is given by Lorentzian structure in the three-dimensional form, or dz square minus dz square plus dx square plus dy square. Here we see the light-like cone where the form is 0, and there are two connected components of time-like vectors. The upper part, which is future-directed, and the lower part, which is past-directed. So the curves should go such that their tangent vectors lie either inside the cone or in the boundary. We cannot go outside the like cone. This is the geometric situation. And now we go further. If we have a Lorentzian structure, then we can define the Lorentzian length of a non-space-like curve. It is defined similarly to the remaining case. We take the integral of the square root of the Lorentzian structure, but now, since the curve is non-space-like, g of q dot is non-positive. So we take absolute value here. You see absolute value. Then we pass to description of Lorentzian distance. Take any points q naught and q1 in M and denote by omega q naught q1 the set of all future-directed non-space-like curves in M. In other words, take the set of all admissible curves that connect q naught to q1. Then the Lorentzian distance, or in other words, time, it is called time separation function from q naught to q1, is defined as follows. If omega q naught q1 is non-zero, is non-empty, that is, if there exists an admissible curve from q naught to q1, then we take the supremum of lengths of all curves, of all admissible curves. And if omega q naught q1 is empty, then Lorentzian distance is by definition equal to 0. One more definition: a future-directed non-space-like curve Q is called a Lorentzian length maximizer if it realizes the supremum in one between the endpoints q naught and q1. This notion, the length and distance, these notions are meaningful in the relativity theory. In particular, the length L of Q is the proper time of a particle Q that moves in the space time M. So suppose that we move in a rocket in the space, and we have a clock in our rocket. This clock measures the proper time of our rocket. So L of Q, given by this integral upstairs, measures the proper time. And the Lorentzian distance from q naught to q1 is the proper time for particles that fall freely under the action of gravity. So if there are no other forces except gravity, then d of q naught q1 is the proper time. So it is the maximum possible time of motion between points q naught and q1. So these two notions, Lorentzian length and distance, are meaningful and quite important in relativity theory and thus in Lorentzian geometry. Now, the simplest example of Lorentzian geometry in the two-dimensional space, the two-dimensional Minkowski flat space-time. So now the manifold is just R2 with coordinates x, y. Here G is the Lorentzian form, and the time orientation is dO over dx. So the blue lines starting from the origin are light-like curves. The red are time-like. They all are length maximizers, and the green hyperbolas. In fact, green hyperbolas are Lorentzian spheres. And the Lorentzian distance is given explicitly by this square root. Okay, now we start to get closer to our problem. What is the Lobachevsky plane? Consider the proper affine functions of the line. So such functions have the form y dot a plus x. So we take a number a and compute the number y multiplied by a plus x, where y is positive and x is arbitrary. We take y positive so that this function be invertible. So we can consider the group. We can consider the group of such functions in the line denoted by G capital. So it is parameterized by the upper half plane of points x, y, where y is positive. So this is our space where our geometry will live. This is a Lie group. The Lie group structure is induced by composition of affine functions. And on this Lie group, we can consider a left invariant frame of the vector fields x1, x2 given as follows. And if you consider the remaining geometry on this group with orthonormal frame x1, x2, then we obtain the famous Lobachevsky Gauss-Bolyai non-Euclidean hyperbolic geometry in the Poincaré's model in the upper half plane. This is our upper half plane, and we obtain, if we consider remaining geometry, we obtain this hyperbolic geometry. This is the reason why we call this half plane the Lobachevsky plane. But we go further. So we have a Lie group G capital, and then we consider Lie algebra G small. It is spanned by the vector fields x1, x2. This is the non-zero Lie bracket. And we see that G is a solvable non-abelian Lie algebra. In fact, it is the unique two-dimensional solvable non-abelian Lie algebra. It is easy to compute one-parameter subgroups in the Lie group. They are given by these equations. In fact, they are arcs of straight lines. So this point with coordinates 0, 1 is the identity of our group. And here in blue, we draw one-parameter subgroups. So they are straight lines, leaving, of course, the parts of straight lines that live in the upper half plane. Okay. And now we describe the left invariant Lorentzian problem on the Lobachevsky plane. So in order to describe it, we have to define a Lorentzian form G on the Lie algebra. Since we would like to have a left invariant problem, then everything is defined in the Lie algebra. And moreover, we should define a time orientation vector field x naught also in Lie algebra, such that G of x naught is negative. Denote the linear form G naught of x given by G of x, x naught. Then the Lorentzian length maximizers in our Lie group are given by the following conditions. The first condition, G of Q dot is non-positive, means that we take time-like or space-like curves. The second inequality means that the curves should be future-directed. Then we start from the identity of Lie group. We can assume this since the problem is left invariant, and we should come to a given point Q1, and we should maximize the Lorentzian length. Well, there is one important distinction between Lorentzian and Riemannian geometries. In the Riemannian geometry, as everybody knows, we minimize Riemannian length of curves, and here we maximize. In fact, if we defined minimization of Lorentzian length, this problem is trivial, because going along light-like trajectories, we obtain Lorentzian length equal to 0. So the problem of minimization of Lorentzian length is meaningless. But the problem of maximization is meaningful mathematically and also physically. So we will study the problem of maximization of Lorentzian length, like this. Okay. Now this slide shows the statement of the problem for Lorentzian length maximizers as a standard optimal control problem. We write it as follows in optimal control. The equation 2 means that we take a curve Q with velocity given in the frame x1, x2, with some coefficients u1 and u2, which we call controls. And the controls u1 and u2 should belong to the set u capital given by the two equations that we already had. So g should be non-positive and g naught should be negative. We start from q naught, which is identity. We should come to q1 and we should minimize the Lorentzian length. So this is the statement of our problem. And now we parameterize the family of problems. We transform the Lorentzian form into the sum of squares. We have 1 minus and 1 plus with some coefficients a, b, c, d. And the time orientation form is also expressed in coefficients a and b. So all left invariant Lorentzian problems on our two-dimensional Lie group are parameterized by matrices A capital with entries A, B, C, D. And moreover, the determinant of this matrix should be positive. So all problems are parameterized by the component of identity in the Lie group GL2R of real matrix of order 2. Okay, so these are the problems we will study. And the first interesting thing we should consider is the curvature. In fact, as quite straightforward computation gives us the following theorem. A left invariant Lorentzian structure G on our Lie group has constant curvature K capital given by this ratio. So in the numerator, we have the value of Lorentzian form G on the vector field x1. So we see that this numerator can have arbitrary sign. It can be positive, negative, or zero. So since we have a constant curvature structure, then we obtain the following corollary, that any left invariant Lorentzian structure G on our Lie group is locally isometric, either to the 2D dimensional Minkowski space, which we already considered, in the case when curvature is zero. In the positive curvature case, it is the two-dimensional de Sitter space. It is a standard positive curvature Lorentzian space. And in the negative curvature case, it is the anti-de Sitter space. In fact, this corollary gives us a local isometry, but we have constructed in the zero curvature case an explicit isometry of our Lie group to a half plane of the Minkowski plane. Okay, so the situation with curvature is quite simple. So we see that the problem should not be so complicated, and this is indeed the case. So now we describe what is called the attainable set. What is attainable set? We fix initial point, say Q naught, and we take all admissible trajectories that start at Q naught, and we study the set of points reached by these admissible trajectories, and this set is called attainable set. So in this problem, the attainable set is characterized in terms of these three functions: lambda 1, lambda 2, and lambda 3. These are linear functions. And so we obtain the following theorem. The attainable set of our system from the identity from Q naught for arbitrarily non-negative time In fact, in Lorentzian geometry, it is called the causal future of the point Q naught, is given as follows. So it is given explicitly by these two inequalities for functions lambda1 and lambda2. And the proof is quite simple. I will not stop on it. So it is quite simple. I will better consider several particular examples. So the first example of the problem, which I call P1, is given by this matrix A, and the picture in the left shows you the future cone U capital. So this picture in the coordinates U1 and U2, and velocities lie in this blue corner, or in the boundary of it. And so the attainable set is given by this blue domain. So we start from this blue point. It is the identity of our Lie group, and we go along curves with tangent vectors in this blue corner, and we fill this blue domain. So this is the attainable set of the causal future of the point Q naught. Okay, so this is in example P1. Now one more example problem P2 with this matrix A. So this is
Yuri, excuse me, maybe I missed. What is the causal future?
Causal future is the attainable set. It is the same. So we start.
It's a set of attainable points. Yes.
Points. Yeah. So the causal future is the term which is used in Lorentzian geometry. In control theory, we say attainable set. It is the same.
Thank you.
So this is problem P2. The future cone looks upstairs like this, and then the causal future also looks upstairs like this. Of course, it goes to infinity upstairs. So, so this is a corner. And one more example, the problem P3 with this matrix A. So the future cone is this quadrant, and the causal future is also quadrant, but moved upstairs to the identity element. So this is attainable set of the causal future. So the attainable set is characterized in quite a simple way. Now, in fact, the only non-trivial equation here is the problem of existence of length maximizers. As usual in variational problems, the question of existence can be non-trivial, because what we are looking for? We are looking for a curve which minimizes some functional. So we consider a variational problem in infinite dimensional space. So the question of existence can be non-trivial, and it is the case here. So now several words about the general theory. What general theory says about existence of length maximizers in Lorentzian geometry. So consider a Lorentzian structure with Lorentzian form G and future orientation vector field X naught on a manifold M. Not necessarily a Lie group, just a manifold M. Denoted by G plus of K naught or A K naught, the causal future or attainable set, and G minus of Q1, the attainable set from Q1 for arbitrarily non-positive time. So the attainable set in negative time. In other words, it is called the causal path of point Q1. And there is a classic theorem going back to 60th years of the previous century, which says the following. Let GX naught be globally hyperbolic. So let our Lorentzian structure satisfy the following two conditions. First condition says the following. Any point Q in M has a neighborhood O such that no future directed non-space-like curve that leaves O ever returns to O. So what do we have here? Take any point Q. It has a small neighborhood such that any trajectory either belongs to O forever, or if it leaves O, then it never returns to O once more. So this is property 1. And second property is the following. For any points Q0, Q1 in M, the intersection of causal future of Q0 with the causal past of Q1 is compact. So we take attainable set of Q1 of Q0 in future time, and take the attainable set of Q1 in past time, and this intersection should be compact. Then, if a point Q1 is attainable from Q0 in positive time, then there exists a Lorentzian length maximizer that connects Q0 to Q1. So if these two conditions, 1 and 2, are satisfied, this geometry is called globally hyperbolic, and in this case we have existence. We have existence of length maximizers, of course, if Q0 can be connected with if Q1 can be connected with Q0 by an admissible curve. What do we have with respect to this condition of global hyperbolicity? It is easy to show that all our left invariant Lorentzian structures on our Lie group satisfy the condition 1, the condition of non-return condition 1. But condition 2 is more delicate. Let us distinguish globally hyperbolic Lorentzian structures on our Lie group. So now we work on our Lie group G, two-dimensional Lie group G, and consider a left invariant Lorentzian structure GX0. We call it time-like if the vector x1 is time-like. So, in other words, if g of x1 is negative. And we call the problem space-like if the vector x1 is space-like, etc. Now we have the following theorem, that a Lorentzian structure GX0 is globally hyperbolic if and only if it is non-time-like. So it is globally hyperbolic in the case it is time-like, it is space-like or like-like. These are two pictures that shows the global hyperbolicity. The picture in the left shows the situation in the space-like case. What do we have here? The blue is the initial point, and the blue corner is the future attainable set of the blue point. Now the red point is Q1, and the red corner is the past attainable set. So we can see that the future attainable set from the blue point intersect with the negative attainable set of the red point is the rectangle, which is compact. The picture in the right shows the light-like situation. Once more, we have one attainable set, which is corner with blue edges, and other attainable set is corner with red edges, and they intersect in a rectangle, which is once more compact. But the situation is not the case if the structure is time-like. We showed that in the time-like case, the structure is not globally hyperbolic. So the picture in the left shows that in the time-like case, the structure is not globally hyperbolic. Once more, the blue point is the point Q0. The attainable set is this corner with blue edges. And let us take this red point, which is situated below this dashed black line. So let me take the point Q1 here. Then the attainable set in negative time. Yeah.
Once more, well, the last sentence, because there was no.
Sorry. So take the point Q1, the red point here, which is below this dashed black line. This is the red point Q1. Then the attainable set in negative time is bounded by these two straight lines, and the intersection of two attainable sets is not compact because it has point arbitrarily close to the absolute. The absolute is the axis of abscissa. the line y equal to 0. So the intersection of the attainable sets is not compact. This shows that the group G is not globally hyperbolic. But if, so now let us pass to the picture in the right. If we take the terminal point Q1 above the black dashed line, then once more the intersection of attainable sets is a rectangle, it is compact. So if we take the manifold M, which is intersection of group G with this half plane lambda 3 greater than 0, this half plane is given by the boundary of this half plane is given by this dashed black line. So this manifold M intersected with this half plane is globally hyperbolic. So we have no existence in the left situation, and in the right situation we do have existence. Okay, so now we summarize our results on existence. What do we have on existence of length maximizers? Item 1, let the group G be non-time-like. Then a Lorentzian length maximizer exists for any point Q1 which is attainable from Q0. And if the D group G is time-like and Q1 belongs to Q1 is attainable from Q0, then a Lorentzian length maximizers exist if and only if Q1 is in this manifold M, which is Lie group G intersected with the half plane lambda 3 greater than 0. The proof is quite simple. I will skip it. Okay, so I better explain what takes place in this picture. So this picture shows the reason of non-existence of Lorentzian length maximizers in the time-like case. Let us look at the picture in the left. So once more, the blue point is the initial point, and the red point is the terminal point. And we see that there is admissible trajectories of the following form. First, we go along the blue line, which is light-like. Then we go along this green dashed straight line, and then we go along the red light-like curve. This green dashed line can be taken arbitrarily close to the absolute. And if we go along this green line, then the time of motion becomes bigger and bigger. So the Lorentzian length becomes big and big, and it tends to plus infinity. So we can choose admissible curves with the length as big as we wish. So there is no existence of length maximizers in this case. A more interesting situation is in the case where the terminal point, red point, Q1, is in the dashed black line here. Then we also have no existence, but the proof is quite distinct. So this picture shows you the network of extremal trajectories. Extremal trajectories are trajectories given by necessary optimality condition, the Pontryagin maximum principle. And I will describe it in several slides, but Pontryagin maximum principle says the following: if there is an optimal trajectory, then it is extremal. And this picture shows you the green curves are extremal trajectories starting from our initial point. And you can see that there is no extremal trajectory that starts at the blue point and comes to the red point. So there is no extremal trajectory from blue point to the red point. So there is no optimal trajectory. There is no length maximizer. So this is the proof of non-existence of length maximizers in this critical case when the red point is on this dashed black line. Okay, so now the question of existence of length maximizers was solved. Let us pass to the search for optimal trajectories in the case where they exist. First, we describe extremal trajectories. as I have said, extremal trajectories are those that are given by Pontryagin maximum principle. Pontryagin maximum principle is a necessary optimality condition of the first order, and so in optimal control theory, when we solve optimal control problems, we do it the same way as we are taught at the first year of calculus in university. Recall that when we are looking for a minimum of a univariate function, how do we do? We look for critical points where the derivative is equal to 0, and then we distinguish true maxima or minima or inflection points with the help of a second derivative. So we first take candidates for maxima and minima. There are critical points, and then we distinguish true maxima or minima. Similarly, we work in optimal control theory. We take candidates for extrema. They are called extremal trajectories, and we find them with the help of Pontryagin maximum principle, which is the first order optimality condition. And then we distinguish true maxima or minima with the help of second order optimality conditions. So what can we say about extremal trajectories? We proved the following theorem. Item 1. We described all extremal trajectories in the following way. Any time-like extremal trajectories is an arc of a hyperbola with an asymptote that is parallel to a light-like one-parameter subgroup, or it is a rectilinear segment. So extremal trajectories are either hyperbolas or straight lines. This is in the time-like case. In the light-like case, the light-like extremal trajectories are arbitrarily Lipschitz reparameterizations of light-like one-parameter subgroups. So in the light-like case, we can go arbitrarily along light-like one-parameter subgroups. So these are extremal trajectories. They are either hyperbolas or straight lines. What about the optimality? It turns out that optimality is characterized in a simple way by item 3, which says that any extremal trajectories is a Lorentzian length maximizer. That is, any extremal trajectory is in fact optimal. And item 4 says the following. If the point Q1 is in the interior of the of M, I recall that M is the half plane of our Lie group given by the function lambda 3, which is the part of the plane which lies above the dashed black line. So if Q1 is in the interior of this half plane in the time-like case, or Q1 is in the interior of the attainable set in the non-time-like case, then there exists, in fact, a unique arc-length parameterized Lorentzian length maximizer connected to Q0 and Q1. So in generic case, the Lorentzian length maximizer is unique. The proof is the following. First, we describe extremal trajectories with Pontryagin maximum principle, and we show that all extremal trajectories are in fact optimal with the use of the global diffeomorphism theorem due to Adamar. This theorem says the following. Suppose that we have a smooth mapping between two smooth manifolds of the same dimension. And suppose that this mapping is non-degenerate, that is, the rank of differential is maximum. And suppose, moreover, that this mapping is proper, that is, the inverse image of a compact is compact. If the manifolds are connected and simply connected, then this mapping is a global diffeomorphism. So we apply this Adamar's global diffeomorphism theorem in order to prove item 3, that all extremal trajectories are in fact optimal. Great. Now we return to geometry. We describe first the Lorentzian distance. We consider Lorentzian distance d of Q naught Q, where Q naught is the identity of our Lie group, so we denote it by just d of Q. So this theorem in this slide shows the properties of this function d of Q. So d of Q is the function on our Lie group G. Item 1 says the following. In the time-like case, the distance function is real analytic in the interior of the half-plane AM, and it is continuous in the closure of this half-plane. Moreover, we proved the two-sided bound, so the distance is bounded by 0, naturally by 0 from below, but it is bounded also by the number pi from above, and the distance at the dashed black line, which is the boundary of M, is equal to pi. And if the point is outside of the closure of M, then the distance, Lorentzian distance, is equal to plus infinity. This corresponds to the case when there is no Lorentzian length maximizer. We have seen a picture where there is a dashed green line along which the length can be arbitrarily big. So in this case, the distance is equal to plus infinity. So this is non-trivial situation in the time-like case. In the non-time-like case, the situation is more simple. Then the Lorentzian distance is real analytic in the interior of the attainable set, and it is continuous in the attainable set. Moreover, it is finite, so we obtain a two-sided bound of the following form. Now, what can we say about the properties, analytic properties of the distance near the boundary of the attainable set, or near the boundary of this half-plane M? Item 3 explains the situation. Near smoothest points of the angle DM in the time-like case, and near smoothest points of boundary of attainable set in the non-time-like case, the Lorentzian distance d is a Hölder function with exponent 1/2 of the Euclidean distance to the corresponding bound. This is quite similar to the analytic properties of the Lorentzian distance in the Minkowski plane. In the Minkowski plane, you recall, the Lorentzian distance is given by the square root. So it is Hölder function with exponent 1/2. The same in our problems. Moreover, we obtained an explicit formulas for the Lorentzian distance d in elementary functions in detail, in inverse hyperbolic functions in the time-like case, in inverse trigonometric functions in the space-like case, and in terms of square roots and rational functions in the light-like case. I will show you the situation in examples. Now, what can we say about Lorentzian spheres? We have Lorentzian distance d, and Lorentzian spheres are defined similarly to the remaining case, or just similar to general metric spaces. So this is sphere of radius r. And theorem describes these spheres. The Lorentzian spheres are non-compact in both directions arcs of hyperbolas for the time-like case, and in this case, radius varies from 0 to pi, and for the non-time-like case, radius takes values from 0 to plus infinity. In the time-like case, this sphere of radius pi is the boundary of the half-plane M, and there is, moreover, the sphere of radius plus infinity. This corresponds to the points where the length maximizer does not exist. So we described the sphere of radius plus infinity. And item 3 says that in any problem, the Lorentzian sphere of 0 radius is a broken line of two rectilinear arrays, the light-like one-parameter subgroups. So in Lorentzian geometry, there is a meaningful problem of describing Lorentzian spheres not only of positive radii, but also of zero radius and of radius plus infinity. And all they were described here for all our problems. Now, let us consider in greater detail the results in three problems. In fact, these two problems, P1, P2, P3, are shows the possible qualitative properties of all four-dimensional, four-parameter family of problems. We have problems, Lorentzian problems, parameterized by matrices A, 2 by 2 matrices. So we have four parameters, but qualitative behavior is described by just by three problems, P1, P2, P3. So the problem P1 is given by this set of control parameters. So this is Lorentzian form G, and G naught is the Lorentzian form G of future time orientation vector with an arbitrary vector. So what do we have in the case P1? Suppose that the point Q1 is in our manifold M minus Q naught. So I recall that M is the part of our Lie group which lies above the dashed black line where we have existence. So suppose that the terminal point Q1 is in M minus Q1. Then we obtained the following formulas for length maximizers. Item 1, if x1 is equal to absolute value of y1 minus 1, in fact, this means that the point lies at the boundary of the attainable set. Then the maximizers are given by exponentials. And the distance, Lorentzian distance, is equal to 0, because we can go along light-like trajectories. If the point is inside, then we have obtained the following formulas for length maximizers given by trigonometric functions, and the maximizers are arcs of hyperbolas given by these equations. These are illustrations for the problem P1. This blue point is our initial point Q naught. The blue straight lines are light-like trajectories starting from initial point. The green hyperbolas are Lorentzian length maximizers. And the picture in the right shows the Lorentzian spheres. So this blue point is the center of all spheres. The spheres of radius 0, the sphere of radius 0 consists of these two blue light-like trajectories. The spheres of radius from 0 to pi are red hyperbolas, like this. So red hyperbolas are spheres of radius from 0 to pi. The sphere of radius equal to number pi is this line. It is given by this dashed black line, and the blue set is the sphere of radius plus infinity. So this corner is the Lorentzian sphere of radius plus infinity. This picture shows the plot of the Lorentzian distance as the function in the Lobachevsky plane. So we have the half plane, and if the point is outside of the attainable corner, then the distance is by definition equal to 0. So we see this flat part of the plot. Here the distance is equal to 0. If the point is attainable, then the distance varies from 0 to the value pi. It is equal to pi at this edge. And if the point is inside of this triangle, in fact, it is a corner, then the distance is equal to plus infinity. And you can see that near the boundary of the attainable set and of the set M, the Lorentzian distance is indeed Hölder. It is not Lobachevsky. The plot has a vertical tangent plane. It is Hölder with the exponent 1/2. Okay, so this is problem P1. Let us consider problem P2. So we consider another Lorentzian form, U1 square minus U2 square, G0 equal to minus U2. Then we have the following description of length maximizers. So here we have existence. So suppose that the point Q1 is the attainable set minus Q0. Then item 1, if the point is in the boundary of the attainable set, then the maximizers are given by the exponents and the distance is equal to 0, similarly to the previous problem. If x1 equal to 0, then the maximizer is a straight line parameterized by the exponential as follows, and the distance is equal by the natural logarithm. And if absolute value of x1 is from 0 to y1 minus 1, then the maximizers are given by hyperbolic functions and by hyperbolic functions. And the maximizers are the length maximizers are arcs of the hyperbolas given by these formulas. Okay, now let us look at the picture. So the left picture shows the Lorentzian length maximizer. So this is our initial blue point. The blue lines are light-like. The green are time-like length maximizers. The picture in the right shows the Lorentzian spheres. The two straight lines, blue ones, are make a sphere of radius 0, and spheres of positive radius are these hyperbolas. So we have here spheres of radii from 0 to plus infinity, not including the limit. So these hyperbolas are spheres of arbitrarily positive radius. So this picture shows the plot of the Lorentzian distance. In this case, we see that if we are outside of the attainable set, then the distance is 0. So here we have the flat part of the plot, and if we are inside, then we have a surface similar to a cone, like this. And this cone grows from 0 to plus infinity. And near the boundary, once more, we have a Hölder analytic description of the distance. And finally, consider problem P3, when the form is G is minus U1, U2. Then once more we have existence. So if the point Q1 is the attainable set minus Q0, then we have the following. Item 1, if the point is in the boundary, in one boundary of an attainable set, then the minimizer is a straight line parameterized by exponential. If it is in other boundary, then it is also a straight line given by this linear function. And generically the length maximizers are given by linear functions or and rational functions like this. And these maximizers are once more arcs of hyperbolas given by this simple equation. And what figures do we have in the left? We have the plot of Lorentzian length maximizers. These green curves are hyperbolas. In the right, we have Lorentzian spheres. One small Lorentzian sphere of 0 radius is made of these two blue rays, and Lorentzian spheres of positive radius are hyperbolas. And this picture shows the plot of the Lorentzian distance. We have 0 distance outside of the attainable set, and here we have a smooth, in fact, analytic function. Lorentzian distance is analytic inside, and Hölder with exponent 1/2 near the boundary. And the distance grows from 0 to plus infinity in this case. Okay, and the last question which I would like to describe is about isometries. So first definition, I recall a vector field X is on a Lorentzian manifold MG is called a killing vector field or just an infinitesimal isometry if the Lie derivative of the Lorentzian form G along the vector field X is equal to 0. So these are infinitesimal isometries. And let us denote by I of M the Lie algebra of killing vector fields. The killing vector fields form Lie algebra, and let us denote it by I of M. And we have described this Lie algebra in all situations. So item 1, in the case of 0 curvature. If the curvature is equal to 0, then the Lie algebra of killing vector fields is isomorphic to the Lie algebra SH2 of the Lie group SH2 of hyperbolic motions of the plane. This is a three-dimensional solvable Lie group, and SH2 small is its Lie algebra. So we have three-dimensional Lie algebra of killing vector fields in the case, in the 0 curvature case. And if curvature is non-zero, then the Lie algebra of killing vector fields is isomorphic to Lie algebra SL2 of the Lie group SL2 of unimodular matrix of order 2. So it is also three-dimensional, but Lie algebra is different. And now what about global isometries? Denoted by I capital of M, the Lie group of all isometries, I mean global isometries of a Lorentzian manifold M. That is, what is an isometry? What is an isometry? As usual, it is a diffeomorphism that preserves the Lorentzian distance. And the group of all isometries we denote by I of M, and denote by I naught of M, the connected component of the identity in this Lie group. In fact, it is known that all isometries form a finite dimensional Lie group, and and we described this connected component of identity in our situation. We have proved the following proposition: the connected component of the group of isometries of our Lie group is given by the left shifts in this Lie group. In fact, it is obvious that it is isomorphic to the Lie group itself. So the group of Lie group of all isometries is two-dimensional. What is the reason why we have three killing vector fields? Why we have three infinitesimal isometries and only two global isometries? Because not all of these infinitesimal isometries are complete. Global isometries should be given by complete vector fields. A complete vector field is a vector field that does not blow, that has trajectories defined for arbitrary times, from minus to plus infinity. And it turns out that of these three killing vector fields, one blows, and it is not complete. And of course, left invariant vector fields are complete. So this is the reason of this distinction in the dimension. Okay, so I think that I'm close to the end of my talk. So now I would like to make some summary. We consider all left invariant Lorentzian problems on the group of proper affine functions of the line. This is the Lobachevsky plane because it gives the Poincaré upper half-plane model of the Lobachevsky geometry. So we consider on this two-dimensional Lie group all left invariant Lorentzian problems. We showed that all these Lorentzian problems have constant curvature, and curvature can take arbitrarily real numbers from -infinity to +infinity. Then we studied controllability or attainable set. In fact, a system is called controllable if given any 2 points in the space, we can connect them by admissible trajectory. And it turns out that in this situation, we have never controllability, and we described attainable sets. Then we passed to the question of existence of length maximizers. Also, this question is not trivial. Existence is guaranteed not always, and we characterized cases when we have existence and when we have not, no existence. Then we described extremal trajectories. We show that they are parameterized by elementary functions, and we obtained explicit parameterization. And then we studied the optimality. We show that all extremal trajectories are optimal. This means that there are no, for example, conjugate points. A conjugate point is a point where extremal trajectories are tangent to the envelope of the set of all extremal trajectories. So there are no conjugate points and no cut points. A cut point is a point where extremal trajectories loses its optimality. But here we have optimality till infinity. Then we constructed optimal synthesis. What optimal synthesis is a rule that for each terminal point Q1 gives a optimal trajectory, a Lorentzian length maximizer that goes from Q0 to Q1. So we constructed explicitly optimal synthesis, and then we described the important geometric notions, described Lorentzian spheres and Lorentzian distance. All they are parameterized by elementary functions. And finally, we described infinitesimal and global isometries. Well, so I think that here I stop. What questions remain here for future research? Well, we have shown that technique of optimal control theory can be efficiently applied to Lorentzian geometry. When we wish to study Lorentzian length maximizers, Lorentzian distance, Lorentzian spheres, then we can efficiently apply optimal control technique. And we would like to do similar work for other space-times with big symmetry group. Of course, here the situation was quite simple because we have many symmetries. Moreover, we have a constant curvature. So we would like to consider the situation, similar problems for other constant curvature spaces, de Sitter and anti-de Sitter spaces, and also other left invariant Lorentzian structures on Lie groups. And also it will be interesting to go back to relativity theory, which originated Lorentzian geometry. So what it will be interesting to study Lorentzian geometries which are relevant in relativity theory and apply optimal control theory to such relevant models of relativity theory. Of course, they are not so simple, but we hope to try to do this. So I think that here I stop, and thank you very much for your attention.
Thank you, Yuri. Questions, remarks? No.
Can you show the matrix A once again?
Yes, once more, yes. Here it is, here matrix A. So we reduce the Lorentzian form to the sum of square, 1 minus 1 plus. And here the elements A, B, C, D are given by these equations, like this.
U1, U2, what is it?
U1, U2 are coefficients near vector fields x1 to like this. They are what we call controls. So U1, U2 are coefficients near x1, x2.
And x1, x2 are
Basic
vector fields or vector
uh,
fields?
they are basic vector fields, yes.
Something from the Lie algebra is involved here or not?
Sorry, please.
Something from some object from the Lie algebra is involved here.
We of course we in fact we work in the algebra because the problem is left invariant, and we work in this the algebra G small, and the Lorentzian form is defined on the algebra, and the time orientation vector field is also an element of the algebra because everything is left invariant. That's why, of course, we work in the algebra.
Ну, можно я по-русски спрошу?
Да, давайте.
Но если там все левоинвариантно, то обычно ведь переходит к какому-то базису там в точке 1, и все, и он отдельно выписывается.
Ну да, в общем, можно взять в точке 1. Вот есть два левоинвариантных поля, можно написать в точке 1. В точке 1 это будет d по dx, d по dy, не более того. Можно и так.
Так, и все-таки U1, U2 это похоже на числа.
Да, это числа, да. Это числа, да. Да, конечно. Это коэффициенты вот в этом разложении, да. Но, да, это числа, да.
Ну, спасибо. Thank you very much.
Да, пожалуйста.
Спасибо. More questions? No. No, then thanks a lot again. So next time we meet in the Independent University, but of course with broadcasting in Zoom. Everyone is invited. Goodbye, Yuri. Thanks a lot again.
Goodbye. Thank you very much. Thank you. Goodbye. Bye-bye.
Bye-bye.